Good afternoon, everyone. I would like to make this video to replace the math day that 3422 students have to do with the data talk that the 3410 students have to do. Thanks for your questions, by the way. These are good questions about concepts of physical chemistry, and we do want to tie it all together with these questions. So I appreciate we have one more round of Q&A after this, and basically keep asking questions like this, and we will have not just a good review of the book, but a good review of the concepts that we're working on for the test. So I will get to it, and we will describe the three questions that we had. So the first question is sort of general, but it makes a great general point about physical chemistry. How did the early cells manage energy by using membranes and ion pumps? How did concepts like gradients, Gibbs free energy, and membrane potential explain why this was successful? Now, this is a question that can be answered lots of different ways, and the way I'm going to do with this, notice that this is all around membranes. Everything that you're talking about has a division of something into two parts. When you have a membrane, you have a wall. When you have a wall, you have an inside and an outside. And that just having that wall is actually a crucial part of physical chemistry. You have a wall and a battery. You have the salt bridge over the wall, and you have the wire that goes around the wall. You have a wall in early life where you have the cell membrane inside and outside, and then you have walls around organs and even organelles, if you want to look at it that way. There are walls everywhere that we look at. And the thing is, the walls are not perfect walls. There is some movement through them, and when you have selective movement across a wall, you can sort of choose how things move, and that means that you can start to have the intentionality that is life coming across. So the movement of ions across a membrane will create a charge difference, and that's similar to the construction of a battery, and this is exactly the kind of comment I want you to be making. How is a cell like a battery? A neuron is like a battery. There are many ways in which it is not like a battery, but one way in which it is that you have two areas, and they have different characteristics. Because there's a wall between the areas, they can each have certain characteristics that are different from each other, and then depending on the rules, there are certain things that have to be the same. So this is a really big question to answer in specifics. I'm going to let you answer it in specifics, but I want you to think about, where do you see walls dividing an area into two parts, and what can get across the wall versus what is blocked by the wall? It's a key concept to all of physical chemistry, especially to the most recent chapter that we have. So I want you to think about any difference in temperature or concentration of matter can be used to drive an engine. We talked about engines a lot earlier. We talked about the walls and batteries later, and clearly the difference between anode and cathode in a battery can be used to drive the electrical work. An engine is a way of doing mechanical work. And what the concept I want you to get here is, as long as you have a separation of two areas, you can actually use that separation. If it will naturally flow from one area to the other, you can use that to catch energy. Now, not all the energy is going to be available. Some of the energy is going to be tied up in just the entropy of the substance at that temperature. When you get to but only a certain amount of the energy is going to be free. That means that you're going to be available to capture it as work. When you release the wall and you let the two things cross into each other. So if you have a difference in temperature or concentration that is a potential, not exactly a fuel cell, but it's a source of energy that can power useful work. The amount of useful work you can get out of it is actually the free energy, which is the total energy. Subtracted from that, you take out the energy that has to stay in the system when it's done, no matter what. For instance, the entropy is a form of energy that has to stay in the system once it's done. These are big concepts, and so I feel like it'd be better to talk about these with equations, but I do want you to talk about these with sentences. And so I'm going to leave this. There's even been, so whenever you have a difference in temperature, you could have a geothermal plant that sits on that difference in temperature and harnesses the energy that is free from the temperature moving from the hot sink to the cold sink, and catches that movement and turns it into useful work. The free energy is the theoretical energy that is maximally available that you could catch from that process of the difference being dissipated. Okay? Really cool concepts here that I really want you to tie everything to. So I want you to think about even when you have salt water and fresh water coming together, there are people who talked about using that difference to drive an energy-related plant, to use that difference as a battery, like a concentration cell. The last thing I'll mention, concentration cells were actually mentioned in lecture. You can have a difference in energy that just comes from having a difference in concentration. So there are people who have actually proposed a form of geothermal energy that doesn't come from hot and cold magma, hot magma driving steam like most geothermal does. It actually comes from an estuary where you have, in a sense, the fresh water is either the anode or the cathode. I don't remember which way it goes, but there's electrodes at the fresh water concentration and at the salt water concentration. And the natural dissolving of the salt into the fresh water will actually drive work that can drive an engine that is based on sticking two electrodes into those different parts. And realize when we're talking about work, we're not technically talking about a regular engine here. We're talking about the work of electrons moving from one place to another. But it's all charged particles times force times distance. Those three things are fundamental concepts that have run through the entire class. So just think about how if you have a geothermal plant, how does that work? If you have any kind of temperature difference, how do you get a Carnot cycle out of that? And if you have a concentration difference, how do you get an electrical current out of that? These are all related to this question. So, now question number 2. I am wondering how early bacteria got oxygen at all prior to photosynthesis. I know fermentation is common in oxygen-poor systems, and fermentation is just rearrangement of bonds to make something more stable, and the bacteria gets energy out of that. Realize this is actually the same concept. We're talking about moving a reaction from a higher energy to a lower energy sort of state or structure, and catching the energy that comes off of that, like a hydrothermal plant catches the water energy that goes through the dam. Lots of similar concepts here. But so fermentation was possible, but if there wasn't any oxygen at all before photosynthesis, how did bacteria get enough oxygen to build an entire cell? Now, this is where it would help to have an equation, because the actual equation is not that there wasn't any oxygen at all, but there wasn't any free atmospheric oxygen. There wasn't O2. There was oxygen in one form. H2O has oxygen in it. It's just not O2. You can actually get O2 out of H2O, or maybe you don't need O2. Maybe you need a reactive oxygen species like OH radical or something like that. Basically, there's lots of reactive forms of oxygen. It's not all about O2. And you can actually, some of the same processes that could make reactive oxygen species could eventually lead to the making of O2. And once they did that as a product, then it would become available for other processes to use. And that's exactly what the rationale is about photosynthesis. Remember, there's a possibility that photosynthesis first developed on H2S, making S2 out of it, and then it would work also on H2O, making O2 out of that. Even though that's harder to break apart, once it's worked out for H2S, it's actually structurally very similar to what you need for H2O. So that's one of the ways it can start. It could start with something that is like water. You can get oxygen out of anything that has oxygen in it. It's just there's some of them that are very hard to break the bonds in the first place. Like alumina rock is very hard to break the oxygen aluminum bonds. So it's locked up in that. So there's a whole bunch of things here, but H2S is something that was very prominent. I think it's a very logical possible beginning for photosynthesis, which starts with H2O. You can do the easier thing first, and then you do the harder thing later. And so there's lots of ways that you could get oxygen. Realize that and there's lots of things we don't know about geology. For example, today I just read a paper, I haven't looked into it in detail. They found that near vents there is a surprising amount of O2 sometimes. And they call it dark oxygen because it's being produced somehow by some kind of chemical reaction deep in the ocean away from the sun. It's not being produced by light, but it's being produced by some reaction that produces the oxygen there. Fascinating idea. So maybe there was a little bit of dark oxygen and there was actually O2 that was able to be used. If you're not using it for everything, if you're not breathing it in and using it to power your entire metabolism, you can do a little oxygen reaction on the side and you can make that work out. And there are little oxygen reactions on the side that happen a lot. In fact, the most common metal, iron, will actually make reactive oxygen species from water. And these will react with anything, but if you're just a cell and you don't really care about living to be 100 years old, the cell can make this sort of reactive oxygen species that will blow up some cells, but occasionally there'll be a cell that doesn't blow up and is able to use the blowing up as a form of energy. So realize that for unicellular cells, they could do the live fast, die young thing, and then they make the O2 that is actually safe enough, it's reactive enough for us to use for energy by breathing it in, and it's safe enough for it to fill the atmosphere and doesn't like react with our skin and stuff like that. Realize that these are all relative terms, but this is the way you want to think about things. And instead of having a comment, I had a second question. So I'm very happy to answer a second question. There's a question about how uneven oxygen distribution would affect geographic formation of early life. This is an interesting question for high versus low altitude, and maybe we could even look at high versus low altitude today. Same proportion of oxygen, but it would be different pressures, so lower partial pressure of oxygen. One of the things that Williams assumes is he assumes that everything's in equilibrium with the ocean. That there's because dissolving is such a fast process relative to rock making or evolution, that you can pretty much assume that everything that can dissolve the oxygen will flow across the planet, and that's fine for a low altitude first level assumption. But I would say that your question could be applied to high altitude life. We could look at about how that's different, and we can look at uneven oxygen distribution today to have ideas of how that affects life in general. Big question, but a very interesting question. The biggest distribution would be in the ocean versus not in the ocean, and then it would be a question of what is the atmospheric composition at that time. The ocean does not dissolve oxygen much, so even today, the ocean is kind of a low oxygen environment. There are certain things you can't do in the ocean because there's not enough oxygen to do them. And so thinking about that, we would look at altitude differences, we look at in the ocean versus not, and we think about dissolved ocean. It's one of the things that geologists measure when they look back at life. They estimate dissolved oxygen levels. And so something people are thinking about, uneven oxygen distribution is obviously a big thing, but when you're talking about the biggest picture, the biggest scale, the local distribution of life is a secondary question to the global distribution of these things, especially because chemical reactions like flows of gases and dissolving of salts tends to be very fast relative to the slow processes of geology and evolution. And I also want to put this together with the different colors of Earth concept from A World from Dust. Probably some of those colors are kind of outdated, but I do want you to think about how there are global changes and then there are local changes. The fact that we have anaerobes at all right now suggests that they are able to hide away. They are able to be a local environment in an oxygen-poor region. So that it definitely would affect things. It's just that it would kind of affect everything. And so our last question is about Chapter 8, and it's how does the transformation of calcium compounds, like the formation of shells in bones, heating of limestone, show how enthalpy changes control whether calcium stays solid or dissolved? And I'm going to focus on the question of heating shells to make calcium carbonate, heating calcium carbonate to make carbon dioxide and CO, because number one, it's a very simple reaction, and number two, when you involve water in dissolving, you start to get more reactions. It starts to get complicated. Not impossible, but complicated like the Mentos and Diet Coke complicated. So I'm going to keep this simple because I don't have a whiteboard and I'm just using words. So let's just talk about the calcium carbonate being heated. Another reason why I like this reaction is because we can actually look it up in the tables. I looked it up in the tables, not knowing anything else about it. We have the reaction CaCO3 arrow, CO2 gas plus the CaO solid, okay? The nice thing about that is you don't have to have any stoichiometric coefficients. It's a perfectly balanced reaction as it is. And so we can just look up the heats of formation. Everything's in its standard state. And so we can look up the standard heats of formation and do a really quick calculation that I can even do in my head. I didn't even use a calculator for this. I just estimated. So I looked up the CaO heat of formation, negative 634. I looked up the CO2 heat of formation, negative 393. I added those together, get negative 1034, approximately. I'm doing this in my head. Those are the product's formation enthalpy. To calculate the overall delta H for the heating of shells, then you have 1034 kilojoules per mole. Those are the products, and those are negative, minus negative 1200 kilojoules per mole. Again, I'm taking this approximately to do it in my head, and I come up with a positive 1066 kilojoules per mole. You're totally right. It's an endothermic reaction, and if you heat the shells, you will be able to put the energy in and break the bonds. You have more stable bonds, and you're actually rearranging them to make less stable bonds. The way that you're able to do that is by putting energy into the system to break the stable bonds and then let less stable bonds form. But they don't know that they were once more stable. They're just atoms, and they form the bonds that they do. And then you have your CaO. So you can make lime, very useful material, from shells just by heating them enough. And it's endothermic, but not terribly endothermic. It's about 166 kilojoules per mole. And that's the kind of thing you can probably reach with a regular fire. There's a few other things I have to think about to be sure about that, but it was in Dr. Stone, so I believe about it. So this is all coming from this reaction being in Dr. Stone to break it up into calcium oxide and carbon dioxide, endothermic, lots of energy. So there's a great comment, and the reasoning is right. You can look it up. You can calculate from heats of formation to confirm that this is an endothermic reaction. But realize that sometimes there are reactions that you are heating to get to happen, not because you are rearranging it to a less stable final state. Sometimes you have to get over a high energy state that is not the product state, but it's a transition state. Sometimes you are heating things and you're actually ending up getting to a more stable state, but sometimes you heat exothermic reactions to make them go. That's a kinetics issue, and this is a great concept for this chapter for you to remember that this one worked out nicely to be endothermic. You can also heat high transition state energy reactions to activate kinetics with temperature rather than activating an endothermic reaction. So just remember, kinetics is not at equilibrium. Shells are at equilibrium, and one of the things about shells, they are not living structures. They are crystals extruded by living structures, and so they do need to be at equilibrium. Structures inside life do not have to be at equilibrium. Life can be maintaining them against the pull of entropy. So life is not at equilibrium inside, but the shells are stable crystalline equilibrium structures outside the living creature, and therefore your reasoning about being endothermic is completely applicable. Just realize sometimes it's kinetics, and if you're talking about metabolism, you might be talking about kinetics. Since you're talking about basically dead shells, you're talking about equilibrium, and it's a lot easier to do physical chemistry at equilibrium. And so we do it when we can. This is a great example of that. So good thinking, everyone. Good questions, and I hope you see how these will relate to the test. So you might want to review this before the test because we got a couple weeks before that. But in between, I watch the rest of the data talks, and we will be back in class on Wednesday to start Chapter 11. We'll be moving on to the big cosmological questions of energy and light. All right, so I'm eager to talk about that as well. And we will get to that and talk about this then. See you then.